Let's take a look at a few more concepts and examples from 2.5. Let's just look at a quick example here right off the bat, and I want to look at taking another limit as x approaches, well, let's say x approaches negative infinity, and let's say we want to do x cubed plus 2x minus 5 divided by x squared plus 4. Now we said before, I think I misspoke earlier in a previous example, I said we're going to divide by the highest power of x we see anywhere, but that's not true. We want to divide, as the book says, by the highest power of x that we see in our denominator, which is x squared. So I'm going to multiply by 1 over x squared and 1 over x squared both on the top and the bottom here. And let's take a look and see what happens. As I distribute this through, what are we going to get? We're going to get the limit as x heads off. I think we wanted to go to negative infinity. Let's go to negative infinity just to make it a little bit more interesting. 1 over x squared times x cubed, that's going to leave us with an x, plus 2x divided by x squared will leave us with a 2 over x, minus 5 over x squared when we take a 5 times 1 over x squared. In our denominator, when I distribute 1 over x squared times x squared plus 4, I'm going to get 1 plus 4 over x squared. Now what happens here as x heads off to negative infinity? While the denominators, this, and this term are all going to get huge, thus these are all going to go to 0. So what do we get? Well, we're going to get the limit as x approaches negative infinity of x over 1. Well, let's see what happens here. Well, as x gets bigger and bigger in the negative direction, divided by 1, x over 1 is, well, that's the same as x. And this is just going to head off then to negative infinity. So it's possible rather for a function to have a limit as x approaches either positive or negative infinity come out to be positive or negative infinity. And the book talks about this by saying these are infinite limits at infinity. So we could have basically 4 types of infinite limits at infinity. We could have the function, actually we want the limit here, we can have the limit as x goes to positive infinity of f of x come out to be positive infinity. We could have the limit as x goes to positive infinity of the function come out to be negative infinity. We could also have the limit as x goes to negative infinity. Let's see here, having a little trouble writing. Negative infinity of the function. That could either go to positive infinity or the limit as x approaches, well, as x heads off to negative infinity. The function itself also goes to negative infinity. Keep in mind again that these infinities, when we write them, these aren't points that we're plugging in. These aren't values. These are saying a different thing. We're saying as x gets bigger and bigger and bigger, the function itself gets bigger and bigger and bigger. In other words, let's just take a look at this first one right here. This is saying we can make the function get as big as we want, arbitrarily large, by just making the x value in the function sufficiently large in the positive infinity direction. This one here, for example, says we could make the function come out to be as big as we want as long as we make x sufficiently big in the negative direction. Now, one of the functions that they look at that has a limit as x goes off to infinity of infinity is e to the x. If you look at f of x equaling e to the x, we can see that the limit as x heads off to infinity of e to the x is in fact infinity. As we remember what the graph of e to the x looks like. Let's delete that one, let's edit that one, and let's say e to the x. There's our graph. You can see the limit as x heads off to infinity of e to the x is infinity. As the x values get bigger and bigger and bigger, the function gets bigger and bigger and bigger. We can make e to the x get as big as we want by making x sufficiently large. You want to get to 1,000,000? You can do that. Just let x be big enough. You want to get to 10 million, million, whatever, you can get there by letting x be sufficiently large. But notice also that for the function e to the x, and for any exponential function for that matter, we have a horizontal asymptote of the x-axis y equals 0, and that occurs as x heads off to negative infinity. So we can also see then that the limit as x heads to negative infinity of e to the x is in fact 0. So we have y equals 0 is, remember, a horizontal asymptote. And finally, before we look at some more examples, I do want to point out something that the book points out at the end of this section on the bottom of page 136. If we look at an example similar to that, say the limit as x goes to positive infinity of x squared plus 2x. We do not want to say that this is The limit as x goes to infinity of x squared. Actually, let's make it minus to be a little more interesting. Minus the limit as x goes to infinity of 2x. Now, the limits, by limit laws, we said we could split these things up, but when we're heading to infinity, when we have limits that go to infinity, well, we can't say that this is infinity minus infinity. We don't know what that means. We can't subtract infinities or add infinities in the way we can add and subtract regular numbers, because remember that infinity is not a number that we can reach or we can plug into our calculator or plug into a function. It's just it just means we're getting very, very large. We can get as large as we want. So what we would say in this case is we would say that this is equal to the limit as x goes to infinity of x times the quantity of x minus 2. And this is going to be a big number times a very big number, which is going to be a very big number. So that we could say heads off to infinity for that reason, because this really heads off to infinity times x minus 2, which also heads off to infinity. So their product heads off to infinity. Okay, let's go ahead and take a look at a few more examples out of your section that may help you with your homework. And let's take a look at number 26. 26 is kind of interesting. We have the limit as x heads off to infinity, and it's limit of the square root of x squared plus ax minus the square root of x squared plus bx. So x is heading off to infinity here, a limit going towards infinity. What we're going to do here is we're going to rewrite this function. You can see as x gets big, this function is going to get big, the square root of x squared plus ax, and this is going to get big, the square root of x squared plus bx. And these are just for arbitrary numbers here, a and b. So we have something big minus something big. It's tough to see how that's going to end up. So we're going to use some algebra to rewrite this function that we're taking the limit of in a similar way that they do for the example 6 on the beginning of page 135. So what I'm going to do is I'm going to multiply top and bottom here by the conjugate of the function, which is basically the same thing again with the middle sign changed. So I'm going to take top and bottom by x squared plus ax plus the quantity of x squared plus ax, the square root rather of x squared plus bx, divided by the same thing. So I'm just multiplying here by a well-chosen 1, something divided by itself. That's equivalent to 1, so I'm not changing the value of the function, and thus I'm not changing the value of the limit. And so we can think of this thing as being over 1. What do we get then? We get the limit as x approaches infinity. Now when I take this quantity times this quantity here, so I have an expression times its conjugate, what happens? Well, these two get multiplied together, I get rid of the square root. I have x squared plus ax. The outer two give me a positive, and the inner two give me a negative of the x squared plus bx square root times the x squared plus ax square root of that. So those get canceled out, and I'm left with then a minus the quantity of the square root of x squared plus bx squared, so minus an x squared plus bx here. Alright, all of that then divided by my denominator of the square root of x squared plus ax plus the square root of x squared plus bx. Well, so far so good. If I distribute this negative here through the top, we're going to have the limit as x approaches infinity. X squared minus x squared, well, those are going to add to 0. I'll have an ax minus a bx. So I have ax minus bx divided by the square root of x squared plus ax plus the square root of x squared plus bx. Okay, now what I'm going to do is look at the highest powered term, which really is just x. The highest powered term in the denominator is just x. I have an x squared, but it's under a square root, so I can think of that, the square root of x squared is just x. So I'm going to multiply both the numerator and the denominator here by 1 over x. So let's look at this, how this is going to work. The limit as x approaches infinity. Well, distributing on the top here, ax times 1 over x is just going to leave me with a, minus bx times 1 over x, which just leaves me with b. So far, so good. Alright, well now I'm going to have the square root of x squared plus ax over x minus the square root of x squared plus bx over x. This is going to be equal to the limit as x goes to infinity. Yes, you need to write this limit notation every time you rewrite the function because you're taking the limit. So we have a minus b divided by, well, the square root of x, or x rather, I can think of as the square root of x squared. So x is the same as, you agree, I think, that the square root of x squared is x. So the square root divided by the square root, I can think of this as the square root of x squared plus ax over x squared minus the square root of x squared plus bx over x squared. Alright, we're almost done with this problem here. What do we get then? We get the limit as x approaches infinity of a minus b divided by, well, let's see, what do we have here? We have the square root of x squared over x squared is 1 plus ax over x squared is a over x minus the square root of 1 plus b over x. And somehow this turned to minus. This should be plus down here. Plus, plus, and plus. That's better. Alright, what happens then as x goes to infinity? Well, the denominator gets huge here. This goes to 0. This goes to 0. And we're left with a minus b then divided by the square root of 1 plus the square root of 1, or a minus b over 1 plus 1, or a minus b over 2 is the limit of this function. It took a while to get there, but we got to the right answer. Okay, let's do one more example here, and I think we'll be in pretty good shape. Let's try old number 36. We're asked to find the vertical and horizontal asymptotes of the curve y equals 2e to the x divided by e to the x minus 5. Well, let's see, what do you want to start with? Let's start with our vertical asymptotes. The vertical asymptotes are going to occur where the limit as x goes to a value gives us positive or negative infinity. Well, it's usually going to be where our denominator is equal to 0. Let's just go ahead and start by finding out where is our denominator equal to 0. Where does e to the x plus 5 equal 0? Well, that's where e to the x equals 5. Let's see, what does that mean? This is then the exponent on e to get 5 is x. So x is equal to the natural log of 5. So it looks like we're going to have a vertical asymptote at the natural log of 5. And that value is roughly 1.61. Okay, now let's check this, our limit here. Let's look at this vertical asymptote. Remember, the definition of a vertical asymptote is that the limit as x approaches a from either the right or the left, or just in general, goes to positive or negative infinity. Let's check this. X approaches, our a in this case is going to be the natural log of 5. That's where our function is undefined in the denominator. And so, well, it's 0 in the denominator, so the whole function is undefined. Let's check it as it approaches natural log of 5 from the right of 2e to the x divided by e to the x minus 5. What do we get? We get the limit as x approaches natural log of 5. Well, let's see. From the right, well, what's this going to be? I guess I'm just rewriting it here. I didn't really do anything, but think about what we're going to have. The natural log of 5 is going to go in here. Well, e to the natural log of 5, 2e to the ln of 5. If I plug it in up there, I can do that. I can't plug it in down here, but I can think about what I'm going to get. Coming at it from the right, e to the natural log of 5 itself is going to be 5. So if we're coming at it from the right, we're going to be a little bit bigger than 5. And so we're going to have something small and positive as x approaches the natural log of 5 from the right. So as our denominator gets smaller, we're going to get towards positive infinity here. And the same thing's going to hold as we head towards the natural log of 5 from the left of 2e to the x over e to the x minus 5. Here, we're going to get the same thing on top, 2e to the natural log of 5, which is just 5. So 2 times 5 in the numerator. And here, as we're coming in from the left, e to the natural log of 5, something a little bit less than that, is going to be something a little bit less than 5. And so when we subtract 5, we're going to have something small and negative. So the denominator getting small in the negative direction, getting closer and closer to 0, but negative is going to make the entire thing blow up to negative infinity. Let's check the graph of that. And we can see from this graph we do have this vertical asymptote right here. You can see this vertical line right about y, or x rather, equals 1.6. And you can see as we approach it from the right, we approach the natural log of 5 from the right, the function takes off to positive infinity. As we approach natural log of 5 from the left, the function takes off to negative infinity, just as we had surmised. Now taking a look at the horizontal asymptotes, you can see that it looks like we actually have two different horizontal asymptotes. Looks like as we head towards positive infinity, x does, the function gets closer and closer to maybe y equals 2, that line y equals 2, and as x heads towards negative infinity, looks like the function maybe gets closer and closer to 0, y equals 0. Let's go ahead and check those analytically by taking the limits. So for our horizontal asymptotes, we want to basically look at the limit as x heads off to infinity, and then the limit as x heads to negative infinity. So let's start with the limit heading towards infinity of 2 times e to the x divided by e to the x minus 5. What I'm going to do here, instead of dividing by x, I'm going to multiply both top and bottom by e to the x. So 1 over e to the x and 1 over, if I can write it, e to the x. What do we get then? We get the limit as x approaches positive infinity. Let's see, here we're going to have just 2, and here we're going to have, if we distribute this through, we're going to have 1 minus 5 over e to the x. Now what happens as x goes to infinity here? Well, as x goes to infinity, let's just take a look at, let's pull off to the side here. Let's look at the limit as x goes to infinity of e to the x. X is getting big, so e to the x is also getting big. This heads towards positive infinity. So what we're doing here then is we're doing 1 minus something that heads towards positive infinity. So 1 minus a very big number is going to be a very big negative number, and this thing is going to head then towards 0. Because the denominator is getting huge, the top is staying at 2, so that thing's going to head towards 0 as x heads off to positive infinity. And that jives with our picture. No, it does not, because I did that completely wrong. E to the x goes to infinity, that's true. So the denominator here goes to infinity, which means 5 over e to the x, just of this term right here, heads to 0. So what are we left with then? We're left with this limit going to 2 divided by 1 minus 0, or just 2 over 1, or 2. So let me go over that again. We had, after we distributed this through, we had 1 minus 5 over e to the x. Well, as x gets big, e to the x gets big, goes to infinity, and so 5 over e to the x gets small. The denominator is getting huge, the whole fraction then is getting small, going to 0, so we're left with just 2. Now let's take a look at the limit as x goes to negative infinity of 2 e to the x over e to the x minus 5. By the same algebra we used before, we'll multiply both numerator and denominator by 1 over e to the x, and so we get then 2, the limit, I should say, as x goes to negative infinity of 2 divided by 1 minus 5 over e to the x. But what happens here is x goes to negative infinity. Well, remember, the limit as x goes to negative infinity of e to the x is actually going to be 0. Remember that, because what's happening here? Well, as x gets bigger and bigger in the negative direction, think of this, you got e to the negative 2e to the negative 5. What you got here is the limit, we could say it this way, as x goes to positive infinity of 1 over e to the positive x. Well, let's not do it that way. That's going to be confusing. Just think about it this way. As x gets bigger and bigger in the negative direction, you have e to a negative power. E to a negative power, for example, e to the negative 4th power. Remember, that's 1 over e to the 4th. E to the negative 10th power, that's 1 over e to the 10th. So as we head in bigger and bigger negative numbers here, if we take e to the negative 20th, that's 1 over e to the 20th. As these numbers get bigger and bigger in the negative direction, these fractions are getting smaller and smaller. So the limit as x goes to infinity of e to the x is 0. So our denominator is getting smaller, meaning this whole fraction now is going to infinity. And so now we've got 2 over something very large and negative. Doesn't matter if it's negative or positive, it's going very large very quickly, so the whole thing is heading towards 0. And you can see that's the case here. As we head towards negative infinity, as x heads towards negative infinity, the function heads towards 0. So we have actually 2 different horizontal asymptotes. Positive 2, y equals 2 as x heads towards positive infinity. Y equals 0 as x heads towards negative infinity. So I hope that one makes sense. It's a little bit confusing. Just have to let me know if you have any questions. So the last thing you need then to get started in your 2.5 homework is the password, and the password is treacle. T-R-E-A-C-L-E, and that just means something which is kind of annoyingly sweet. So, like a really sappy movie would be a treacle movie. So something very sweet, annoyingly sweet. Treacle, treacle is your password. Good luck. Let me know if you have any questions.